Okay, welcome to lesson 2 of unit 1. This time, instead of looking at solving linear systems graphically, we're going to be looking at a version called substitution. This is one of the two algebraic methods that you can use to solve linear systems. The first question we want to think about is why solving linear systems by graphing is not always the best. One, we don't know where the POI is going to be. Oops, that was terribly written. So it could be over at, I don't know, 250 and 11. It could be at 35 and 2. It may be off your graph. So not necessarily will you be able to plot the two lines and find the POI easily. Another thing is it could be a decimal. So between 2 points. So it's not always going to be the best method to use graphing. It's good for when the equations are simple and you think you're going to get a nice whole number, but oftentimes we don't get those nice whole numbers. We get evil decimals or fractions, and you can't accurately find out the point of intersection from graphing if that's the case. So oftentimes we use algebraic methods, and this video is going to be looking at the algebraic method called substitution, where one equation is rearranged to isolate for a variable and substituted into the other. Hence the name substitution. You're going to put something in for something else. So your steps are you're going to be first label both equations, one as equation 1 and the other as equation 2. Choose one of the equations and isolate one of its variables. So that's going to be our step 2. Substitute the expression that you have determined in place of the corresponding variable in the other equation. Translation. You're going to take that isolated variable, what it equals to, and shove it where that variable should be in the other equation. You're going to solve the new equation that you've created, and then you're going to substitute the solved value into one of the equations to determine the value of the other variable. Last, this is an optional step, is to check to verify that the order pair you found out is correct, that satisfies both equations by using the left side and the right side check. Again, this is optional. Sometimes I'll ask you to do that specifically just to double check your variables, but other times I'll just say, you're good. So let's do an example here. We're going to solve this system of equations using substitution. So our first step was to label our equation. So here's equation 1 and here's equation 2. If we're looking at this one here, why is solving by graphing not the best example for this method? Let's be honest, we're going to have fractions. You can see that these aren't going to give us nice whole numbers at all, even if we rearrange them in y equals mx plus b format. This is just not going to give us a nice number. So we already know, looking at these equations, that since they're giving us various fractions, we're not going to find a nice number. We're not going to find a nice whole number that these equations will cross at. So we're going to have to use an algebraic method to find the approximately exact number. So looking at these two equations, for which one is easier to isolate, let's isolate x using equation 2 because we can easily take away something and we're only going to get one fraction instead of two fractions. If we use this guy, we're going to have a bunch of fractions. We don't want that. So we're going to use equation number 2 to isolate for x. So we're going to isolate for x. Good. 2x minus 7y equals 4. 2x equals 7y plus 4. and divide it all by 2. Get x equals 7 over 2y plus 2. And this time I'm going to say, let's use decimals. In this case, it comes out with a nice clean decimal, so we don't need to worry about something going to an eternity. So this is a nice clean decimal. So this is our new equation right here. And we're going to be using this guy to sub into one of the other ones. So here what we're going to do is substitute x, which is this expression up here, this expression, into equation 1. So what we get when we're doing this one here, we're going to take 3x, this is from equation 1, plus 4y equals 10. And where our x was in this equation, we're going to substitute in what we have isolated, which is 3.5y plus 2. Okay, going to close off that bracket. Plus 4y equals 10. Well, what we're going to do is expand out our bracket and solve for y. And when we expand out the bracket, we get 10.5y plus 6 plus 4y equals 10. Okay, let's collect our like variables and bring them to each other's side. So if we get 10.5y plus 4y, we get 14.5y. And we're going to have 10 minus 6 on the other side. So that gives us 4. 14.5y over here. And what we're going to do is divide these out. These cancel each other out. And we are left with 0.0275. And it keeps on going. But we're just going to keep this nice small number here. This is one of the few times where it's just easier to take a smaller number. For linear systems, we don't need 100% accuracy. If you did want 100% accuracy, you would keep it as a decimal and not transfer it in, keep it as a fraction and not transfer it into a decimal. But we don't need to be 100% accurate here. So our next step, what we're going to do, is find x. So what we're going to do is take this equation here where we have x equals 7 over 2y plus 2. We're going to sub in for y what we had discovered as being y. So we're going to put the 0.275 ... And what we're going to get is 2.9655. Keeps going on for eternity. But we're just going to take some of it. We're going to round our numbers here. So we got POI. We're just going to keep them to 2 decimal places so we have nice neat numbers. So if we have wrong place, looking at x, we have 2.9696555. What we're going to do is round that to 2.97, and we're going to do the same thing to our other one, to 0.275, rounded to 2 decimal places gives us 0.28. Now this is approximate, but it's good enough. It's good enough. So this is our POI. This is how you do substitution. If you notice what we did here is we first isolated, that's our step. We subbed in a value, and we subbed in a value. This is how you can help remember substitution. You're subbing in values as you go. So let's try another example. This time we're going to be looking at two equations, 4x minus 3y plus 16 equals 0, and 5x minus y equals 2. Our first step is always to label our equations. So we have our first equation here. I'm just going to switch. Here's our first equation. We'll label this one 1 and the other one 2. Now, looking at these equations, we can see which one's going to be an easier one to isolate for. In this case, you can see y is by itself. We can just bring it over to the other side and bring the 2 over. That's going to be a lot easier than trying to isolate anything in the first one. Rule of thumb, figure out which equation is a lot easier to isolate, and that's going to be your best way of not giving yourself a headache and not leading yourself up to have more likelihood of complications because you might have missed a step in the beginning. Always go for the easiest one to isolate. It will save you time and it will save you brain power. So we're going to use our second equation and isolate for y. Again, y is the easiest to isolate for. So we have 5x minus y equals 2. We're going to shove the y to the other side and the 2 to the other side. Just going to swap those out. Let's get 5x minus 2 equals y. Okay, now that we have this, we have an isolated variable. We're going to put that variable, what we've made it equal to, right over here. And we're going to shove it into another equation or substitute it in. Whichever way makes more sense. Whichever words help you remember it is going to be the best way for you to kind of set it up. Remember how to say it to yourself every single time you go to do it. Let me spell substitute properly. For me, it was always easy to remember it by saying, I'm just going to shove it into another equation. If that works for you, go ahead, even write that down. I do not mind. So we're going to substitute in for equation 1. So our equation 1 was 4x plus, sorry, not plus, minus 3y plus 16 equals 0. We can always start rearranging this as we go just to have all the variables on one side as well. So as we're writing this in, I'm going to do that. So I'm going to have 4x and 3, and I'm going to put in where y was the 5x minus 2, close bracket. And I'm already going to put that 16 on the other side as a negative just so we can save some steps over here. So next step is to expand it out, which we get negative 15x plus 6 equals negative 16. Let's start collecting some like terms. We're going to get 11x. I'm going to already bring over that other 6 over to the other side. Get 11x equals negative 22. Let's divide both sides by 11 to isolate for x again. And we're going to get x equals negative 2. Just going to cancel those guys out. So once we have found out our 2, we need now that we found out x equals negative 2, we need to find out what our y equals. So let's go up here, find y. And how are we going to find that? We are going to take negative 2 and place it where the x is in our other equation. So we have y equals 5x minus 2. Where the x is, we're going to put that negative 2, which we found out from our previous one. We're going to expand out, which gives us negative 10, not negative 10, Did I make a mistake over here? Yes, I did. Let me go and fix that. That's a negative 11. That's a negative 11. That becomes positive, and that becomes positive. So that's going to be a positive one. Sometimes we need to double check our answers to make sure we were going right thing. And everyone, note, remember, pay attention to your signs. So 10 minus 2 gives us 8. Therefore, our POI is 2 and 8. So here's a great opportunity for us to check if we got this right. So I'm just going to break this up a little bit over here. And let's do a check to make sure that what we found is correct. So let's do a quick check. So what I'm going to do is do a left side, right side without actually writing the left side, right side. So what we're going to do on this one is we're going to put our values in our first equation. So this is our equation 1, and I just put our values that we had for x and 8 in the respective, x and y in their respective places. So as I find this out, we multiply it out. Minus 24 plus 16 equals 0. If we add that out, we're going to notice it's 0 and 0. So that's good. Check mark. We're good. Now let's try the other question. So we have 5 and 2 minus 8 equals 2. This is using our equation that we have up here. We put the x and y. Then we get 10 minus 8 equals 2. Yep, that does equal 2. Perfect. So that means we did it right. We're all good to go. If the right side and left side for both of them equals the same, we know we did it right. We can just do a big check mark and we're good. All right, so looking at this one, we have over 2, y over 3 equals 3. Now, we don't really like fractions, so there is some ways that we can deal with getting rid of fractions. If we make them all have the same base, aka the same denominator, and multiply out, we can get rid of the fractions. So we're looking at our first one here, x over 2 plus y over 3 plus 3. What we can do is get them all to be a base of 6. I'm just going to rewrite that a bit better. So we need to know what we need to multiply each of these by in order to get them to a base of 6. Okay, a denominator 6. In order to get 2 to 6, we need to multiply by 3. We need to get 3 to 6, we need to multiply by 2. And this is technically over 1, guys. So if we want to get 1 to 6, we need to multiply it by 6, which gives us our new equation of 3x plus 2y equals 18. What we've done is multiply them out so we can eliminate the base, that denominator. This is a way to avoid having any denominators and any fractions. It's a really good way to quickly get rid of them. So we're going to do the same thing for our second equation and create a new equation that we're going to call equation 4. I'm renaming these two different equations just because now that we have multiplied them out by something, we technically need to give them a new equation number because it's not the same as it was before. So the next one we have is 5x over 4 minus y over 4 equals 1. Now, these two guys are over base 4. We don't need to do anything to these because they already have the same base. But we need to do something to 1. Right now it's 1 over 1, so we need to multiply that guy out by 4 in order to get it on a base of 4 like the other one. And if we do that, we can simply knock out these 4s. So we get 5x minus y equals 4. And that is our new equation that we're going to call equation 4. All right, now that we have equations that don't have any fractions, let us start by doing some substitution. So the one that's going to give us the easiest way to isolate with the least amount of effort is if we deal with equation 4. It's a lot quicker for us to quickly isolate. So use number 4, equation 4, and we're going to isolate for y. That way we don't need to do any more division. So we got 5x minus y equals 4. And if we rearrange it, we're going to get 5x minus 4 equals y. And that is our new equation that has been isolated to give us an item that we can now substitute into our other equation. So what we're going to do now is substitute y, our new y, into number 3. Equation 3. So our equation 3 is 3x plus 2y equals 18. And where y is, we're going to put in the equation that we found. So in our brackets now, we're going to put the 5x minus 4, and that equals 18. So we're going to expand out and solve. Collect like terms. Isolate the x now. These two cancel each other out. And we got 2 for x. So now we're going to take that lovely x and we are going to go and find y. That is our next step. Y equals, we got this lovely equation over here that's going to help us find that out. We're going to replace our x with what we found out to be our x, which is 2. 5 times 2 gives us 10, minus 4. Y equals 6. So therefore, our point of intersection is 2 and 6. Alrighty. Those are some normal cases. These ones aren't going to give us any problems. But if you guys remember from our graphical analysis, there are 2 special cases that may not have points of intersection. And it's important that we know how to identify them when we are looking at algebraic systems. So the first special case we're going to be looking at is when we have infinite solutions. So when they are the exact same equation. But we don't see that they're exact same equation when we look at them. But we know that they are the exact same line once we start filling in everything else. So first step is always to label our equations. Nice enough that this one's already isolated for us. So we're just going to shove equation 2 into equation 1 because they're already nicely isolated. Isn't that a treat? We don't have to do anything here. So we're going to use equation 2 and sub it in to equation 1. Get 2x minus y equals 8. I'm going to do a step already just because I don't want to have to deal with distributing it afterwards. So we're just already going to distribute this 2 in. And now let's start subbing in what we need to know. So our y is x minus 4. Got that from our equation 1. Now we're going to expand out. So 2 times x gives us 2x. 2 times 4 gives us negative 8. Okay, let's collect some like terms. Got 0x equals 8 minus 8. 0x equaling 0. Keep the 0. There's an important reason for that in a second. Don't eliminate it. If you start noticing that the variables get eliminated, keep the 0 in front of the x. Because if you get to this point, and you notice it's 0 over 0, this is called something called undefined. If you get at the end an undefined, a 0 over 0, it means you have infinite solutions. So we can say, therefore, there are infinite solutions. You're going to notice this when the lines are the same. So you have your two equations, but they're actually the same lines. That's when you're going to have something that is infinite solutions, okay? You're going to find an undefined x or an undefined y, a 0 over 0. So here's another one. This is going to be an example where there is no solution. In this case, we got y equals 2 over 3x plus 5. This one's nicely isolated for us. We're going to use this guy, and we're going to put it into 2x minus 3y equals 4. So let's go with stating what we have. This is our equation 1. This is our equation 2. And we're going to sub 1 into 2. So you have 2x minus 3y equals 4. We're going to do 2x minus 3. And now we're going to put in this variable, which is 2 over 3x plus 5 and bracket. And this still equals 4. So we expand out the bracket. 3x 3 times 2 over 3x. Those 3's cancel each other out, leaving us with negative x. Just make that negative a bit better. Minus 15, because 3 times 5 equals 15, equals 4. Going to notice 2x minus 2x equals 0x. Now remember, I told you guys to keep the 0. There's a reason for that. We're going to bring this 15 over. We got 4 plus 15. What we're going to notice is we get 0x equals 19. If we have 0x equals 19 or 0x equals something, but it's not a 0 over 0, this is the instant where we have no solutions. It needs to be undefined with a 0 over 0 in order to be infinite solutions, but anything here you have 0x equals something, an actual number, not a 0, that is where you're going to have a no solutions, which means the two lines are parallel. It's important to be able to notice the difference between the two. So that is the end of the lesson. You can do your check, your understanding practice from Waterloo. And then what you guys need to do next is the assigned work. Obviously in this document right now, there's no answers, but in the online post in your Google Classroom, the answers will be posted. All right, guys. So that is our lesson 2 on the first of 2 versions of algebraic solutions for linear systems.